Hello, this is lesson 23 on Chebyshev's theorem. We'll begin with some properties of the normal distribution, which is a bell-shaped distribution. What's the probability that a normal random variable is within 1, 2, or 3 standard deviations of its mean? Now, if we're dealing with the z-score setup, the mean is 0, and the standard deviation is 1. The z-score represents the number of standard deviations you are from the mean. Positive z-score is above the mean, negative is below. So let's look at one standard deviation, a z-score of 1. If we look at that on the chart here, 1.0, and then the 0, 0 column, it's 0.8413. So the area to the left of 1 standard deviation, is 0.8413. Now, if we want to figure out the probability that we're within 1 standard deviation of the mean, we need to get the area to the left of the mean, which is 0 in a standard normal distribution. At 0, the z-score 0 gives you a probability of a half to the left, 0.5. So we subtract those values to get the area in between. So it's 0.8413 minus a half, and that leaves us with 0.3413. Now, that is that's the probability of being between 0 and 1. So that's the probability of being within a standard deviation above the mean. We want to get within, so we have to also do below, but by symmetry, those are the same. We have 34, 34, so that we're going to double that. So the probability of being within 1 standard deviation of the mean in a normal distribution is about 0.68, 34, 34. If you go 2 standard deviations out, you're gaining another 13.5 on each side, which leads to approximately 95%. And if you have 3 standard deviations, it's over 99%. Now, again, this is a special property for situations where you have a variable with a normal distribution bell shape. So the probability of being within 1 standard deviation of the mean when you're dealing with a normal distribution, that's 68%. For 2 standard deviations, it's 95, and for 3, it's 99.7. So to see a concrete example, if we look at height, which is not perfect, but is close to normally distributed, if we look at a set of people, we look at the heights with a distribution that is going to be close to normally distributed, mean 5'9", standard deviation 3 inches. So 68% of the population is within 1 standard deviation of the mean. You subtract and add. 5'9" minus 3 inches is 5'6", plus 3 inches is 6 feet. 68% of the population is within that range, 5'6" to 6 feet. If you go another 3 inches on either side, down and up, 5'3" to 6'3", that's 2 standard deviations, 95% of the population. And if you go another step to 3 standard deviations, that gives you 5 feet to 6'6", 99.7% of the population will lie in between those values. Now, some non-normal variables. Income is usually skewed, and it would be skewed to the right. Fewer people with very, very high incomes, most people bunched up on the lower end. Age of death skewed to the left, where thankfully we have a lower frequency of younger people dying. So those are some examples of skewed distributions that would certainly not fit into the normal bell shape. So just some notation here. The probability that we're within 1 standard deviation of the mean, the absolute value of x minus the mean mu, less than or equal to 1 copy of sigma, is about 0.68. Within 2 standard deviations of the mean, probability x minus mu absolute value less than or equal to 2 sigma, that's 95 about. 3 standard deviations, 99.7. So if we look at this from the opposite point of view, within 1 standard deviation, that's about 68% probability. So there's a 32% chance, roughly, that will be more than 1 standard deviation away from the mean. Please note, when you're dealing with a continuous distribution, the probability of any one single value is 0. So it's okay if we have the equality listed in both of these. What's the probability of being at least 2 standard deviations away? It's 1 minus 95, so it's 5%. And for 3 standard deviations, 1 minus 0.997, it's 0.003. All right, now we move on to some general situations where we don't assume the shape is that of a normal distribution. So here, Markov's inequality, we're given that x is a random variable that takes only non-negative values and a positive number a. The probability that x is greater than or equal to a is less than or equal to the expected value of x over a. And so we have a proof here. So expected value for a continuous random variable integrating negative infinity to infinity x times f of x dx. Now we're told that x takes on only non-negative values. So this is the same as starting the integral from 0. So 0 to infinity, x times f of x dx. That's equal to the expected value. We can split up an integral anywhere in between those limits, 0 to infinity. So we're going to go from 0 to a first, then a to infinity. Now, x is non-negative. A density function, f of x, is always non-negative. So this will be a non-negative expression integrated from 0 to a. This will be non-negative. So we can say that this integral here, fx times f of x dx, is greater than or equal to the second piece. First piece is non-negative. It can only make this, keep it the same or make it bigger. So we have this inequality that this total is greater than or equal to the second piece from a to infinity. So we have the expected value of x is greater than or equal to this integral from a to infinity, x times f of x dx. Now, these limits are on x here, so we can replace x with a here, and that would be the lowest value. So e of x is going to be greater than or equal to integral a to infinity of the constant a times f of x dx. We can factor out the constant a. We're left with the improper integral a to infinity f of x dx, which is the definition of probability of being greater than or equal to the starting point a. So after all that, we have the expected value of x is greater than or equal to a times probability x greater than or equal to a. Divide out by a, we know it's greater than 0. It's not 0. We get what we wanted to show. The expected value of x over a is greater than or equal to the probability of x greater than or equal to a. So the probability that x is greater than or equal to a is less than or equal to e of x over a. Which, again, we don't get an exact value. We get a bound here, but without knowing much about this setup here, all we really know is that the random variable takes only non-negative values and that we would have to know the mean. So an example here, suppose we have a non-negative random variable with mean expected value 100. Let's get an estimate on the probability that x is greater than 130. Which is the same as greater than or equal to if you're dealing with a continuous situation. According to this formula, this will be less than or equal to the mean divided by a 130. 100 over 130 is 10 over 13. It's about 0.77. It's about a 77% chance. Let me rephrase that. The probability x is greater than or equal to 130 is less than or equal to about 77%. So we can say that the probability here is at most, it's less than or equal to 77%. All right, finally, we arrive at Chebyshev's inequality. It's kind of similar to what we saw above there with this 1, 2, and 3 standard deviations for the normal distribution, which is called the empirical rule. So this is now a general situation. We do not need to know if it's normally distributed. So for any shape distribution, the probability that absolute x minus mu greater than or equal to k times sigma is less than or equal to 1 over k squared, where k is representing the number of standard deviations we are from the mean. So if k is 2, the probability that we're more than 2 standard deviations from the mean is at most 25%, less than or equal to 25%. If we plug in k equals 3 and we're dealing with 3 standard deviations, the probability that we're more than 3 standard deviations away from the mean is less than or equal to 1 over 3 squared 1/9. And so we're going to prove this here. First up is a definition here. We're defining this function L of x to be 0 if x is between the mean minus k sigma and the mean plus k sigma. So basically, L of x is 0 if x is within k standard deviations of the mean. Otherwise, L of x is 1. And so this graph here is going to be basically horizontal pieces. So if x is between mean minus k sigma, mean plus k sigma, then we get 0, and it's on the x-axis. Otherwise, if x is beyond those values, larger than mu plus k sigma, smaller than mu minus k sigma, then the value is 1. And so we have horizontal rays at a height of 1 unit. Now we define q of x to be x minus mu over k sigma squared, where k and sigma are constants. K is number of standard deviations, sigma is the standard deviation. We square the top and bottom and square both k and sigma squared. The graph of q is a parabola opening upward. Okay, we have positive coefficient here on x squared term, so it's opening upward. So we're going to use the fact that L of x is less than or equal to q of x. So what happens if you plug in mu minus k sigma? The mu's cancel out. We get a -1 here, negative k sigma over k sigma. -1 squared is 1. So we get that the q function is equal to 1 when we reach that threshold of mu minus k sigma. And so that means that it's going to cross through this open circle here at a height of 1 unit. And the same thing is going to happen at mu plus k sigma. When you do the subtraction, the yes, if you plug in mu plus k sigma, mu still cancels out. This time we would have a positive 1 on the inside squared is still 1. Now, we could plug in some other values to verify what this graph looks like, but we know it's a parabola that opens upward. So as we go farther away from the turning point, we will get larger and larger values here. And based on this format here for Q, we see the shift of mu. So we know that the vertex occurs at mu. So this is a parabola opening up. We know at mu, it's equal to 0. That's our turning point. And if you plug that in, the whole thing becomes 0. And we know that at those edges of the mean minus k sigma plus k sigma, we do hit 1. After that, it's going to get larger because this parabola opens upward. So this is the graph of q of x in green and L of x in red. And we can see from the picture that for any x, L of x is less than or equal to q of x. So we want to get a handle on the probability that x is less than mu minus k sigma, as well as greater than mu plus k sigma, to get those two extreme cases that you're more than k standard deviations away, either above or below the mean. So how do you calculate those probabilities? You're integrating the density. Integrating the density here. So for the less than situation, you're going from minus infinity up to an upper limit of mu minus k sigma, and then for the right hand side, for greater than mu plus k sigma, that's our lower limit up to infinity. Now, the idea is that we can use the L function to describe these two pieces, because the L function is equal to 1 on those regions, and it's equal to 0 in between. So we could integrate negative infinity to infinity on L, and we'd be getting the exact same thing, because it's 0 in between mu minus k sigma, mu plus k sigma. So this probability here of being more than k standard deviations from the mean can be expressed as integral negative infinity to infinity L of x times f of x dx. Since L is less than or equal to q, we can replace that with q. If f is less than or equal to g, the definite integral will follow suit. Definite integral of f will be less than or equal to definite integral of g. So we know that L times F integral is less than or equal to Q times F integral, because Q is bigger than L. Now, what was Q? Q was 1 over K squared sigma squared times X minus mu squared. Yeah, okay. So Q of X is replaced with 1 over K squared sigma squared times X minus mu squared. We still have the F of X from the density. Dx tells us that x is the variable here, so k squared and sigma squared can be factored out in the denominator. And what we're left with here is the definition of variance, because we have the expected value of x minus mu squared. We're integrating that expression times the density. So that is the expected value of x minus mu squared, which is the variance sigma squared. And so we get out that this integral is equal to 1 over k squared sigma squared from the outside. Inside is the definition of variance, another sigma squared. Those cancel out. We're left with 1 over k squared. And so that tells us that 1 over k squared is indeed an upper bound for these probabilities of being more than k standard deviations away. So again, Chebyshev gives us an upper bound, but not an equality. All right, let's take a look at a brief example here. Use Chebyshev's inequality to get a bound for the probability that x is between 20 and 60, given the mean is 40, standard deviation is 10. Now, notice this is between. So it's a complementary point of view. We did the proof for, more than a certain number of standard deviations. So this is going to be less than. So we want to get the probability that x is between 20 and 60, mean is 40. So we're going to do the opposite point of view. We can do it either way. Probability that absolute x minus 40 is greater than or equal to 20, meaning that we're 20 units away from 40, which would land us at 20 and 60. The probability, based on Chebyshev, the probability that absolute x minus 40 is greater than or equal to 2 times the standard deviation, that is at most 1 over k squared, 1 over 2 squared, which is a quarter. So there's a 25% chance of being beyond this interval, outside these bounds of more than 60, less than 20. So by the complementary law, the probability that x minus 40 is less than or equal to 20, absolute value, is the complement, which is 1 minus a quarter, 3/4. So we know that the probability that we're more than 2 standard deviations away is at most 25%. The probability that we're within 2 standard deviations is at least, it's greater than or equal to 3/4, 75%. All right, this concludes our video on Chebyshev's inequality.